fusion process is much greater than the energy released during fission process. Well, let's talk about nuclear fission, which is the most prominent source of nuclear energy at the moment. So that is more important for us. What is nuclear fission? Fission is the process of splitting. So the process of splitting a massive nucleus into more stable, less massive nuclei with the result of releasing energy is called nuclear fission. Now here I have illustrated a fission process. A uranium-235 nucleus, by any chance, if it absorbs a neutron, you see, a neutron going into a uranium-235 nucleus will create great instability. And immediately that nucleus will split into two pieces. And one piece will be rubidium of mass number 90, and the other could be cesium of mass number 143. And in that process, also some free neutrons are released. Now, we will be talking about this as we go on. Now, if you look at that animation, a neutron goes into the nucleus of uranium-235, splitting into two pieces. Now, not always, these may not be always the two pieces. We will see another scenario later on. So this is the simple process of nuclear fission of uranium-235 nucleus. Uranium-235 is called a fissionable material. It is capable of undergoing fission after absorbing a neutron. So fission can occur when the nucleus of a heavy atom captures a neutron. In addition to energy, free neutrons are also released during the fission. Very important, because in order that fission may occur, you need free neutrons that can be captured by nuclei. So if one nucleus of uranium-235 undergoes fission by capturing a stray neutron, that fission will release more neutrons which can then be captured by other nuclei to produce fission. So that concept is very important. So if a neutron is captured by a fissionable nucleus, it splits into two pieces. We call them fission products. And also are released free neutrons. On an average, sometimes 2 neutrons, sometimes 3 neutrons. We would say on an average 3 neutrons are released per fission. Now, materials that undergo fission are called fissionable materials. Now, what are some of the fissionable materials that exist in nature? Well, there aren't very many fissionable materials that exist in nature. Some can be made. Well, uranium-235 is actually a naturally occurring isotope of uranium. Now, remember, most of uranium is the naturally occurring uranium is uranium-238. Uranium-235 is only a very, very tiny part of naturally occurring uranium. Another isotope of uranium is uranium-233, that is a fissionable isotope. And a third fissionable material is plutonium-239. It doesn't really occur naturally, but it can be produced by making uranium-238 radioactive. We will talk about that as we go on. So, 3 important fissionable materials are uranium-235, uranium-233, and plutonium-239. Now, the fission of uranium-235 in reactors is triggered by the absorption of a low-energy neutron. So, the fission is started. In order to start fission, you need low energy, or sometimes they're called thermal neutrons. You need to make those neutrons available to start fission. On an average, as we said, 3 neutrons are released per fission. Now let's look at the fission of uranium-235. Uranium-235 is the chief fissionable isotope used in reactors. Well, in order to produce atomic energy, we build reactors. What is a reactor? We will talk about that later. A reactor is a controlled environment where fission is allowed to proceed, that can be controlled so that energy can be produced and used. Now, here we have an animation. Watch it carefully. A slow neutron is being absorbed by uranium-235. Now, great instability, and there is the product. The product is krypton of atomic mass 92 and barium of atomic mass 142, and also free neutrons. Watch that again. Stray neutron absorbed by uranium-235. Fission occurs, fission products, krypton 92, barium 142, and free neutrons. You see only 2 free neutrons there. Well, in most cases that may be true, but in some cases there may be 3 free neutrons. So this is the process of the fission of uranium-235. Okay. So the fission products are barium, krypton, 3 free neutrons, and of course energy. Now, how much energy? Approximately 200 million electron volts, which is 200 times, well, when I said this is not million, this is million electron volts. Million is the uppercase M. So 200 million electron volt will be 200 times 10 to the power 6 times 1.609 times 10 to the negative 19, and that will work out to 3.22 times 10 to the negative 11 joules for 1 fission. I hope you followed that calculation. Now what I did here is, instead of writing 1 electron volt as 1.609 times 10 to the negative 19 joules, I wrote 1 million electron volt. This is the equivalent of 1 million electron volt. In other words, 19 minus 6. So 200 million electron volt is 200 times this, which is 3.22 times 10 to the negative 11 joules. Now, that is the energy released per 1 fission of 1 uranium-235 nucleus. Now, so if you take 1 gram of uranium-235, how much energy will be released? Can you calculate that? Now, I'm sure you know how many atoms are there in 1 gram of uranium. Well, let's do that. How much energy is released when 1 gram of uranium-235 undergoes fission? The mass of 1 mole of uranium-235 is 235 grams. That's the definition of a mole. So 1 mole of uranium-235 contains 235 grams. That means 1 gram is 1 over 235 of a mole. So the number of moles in 1 gram is 1 over 235. Now, how many atoms are there in 1 mole of uranium-235? That's the Avogadro number. So 1 gram, or 1 mole of uranium-235 contains 6.02 times 10 to the 23 atoms. Therefore, how many atoms are there in 1 gram? That will be 1 over 235 multiplied by the number of atoms in 1 mole, that is the Avogadro number, and that will be 2.56 times 10 to the 21. That is the number of atoms. 2.56 to the times 10 to the power of 21 is the number of atoms in 1 gram of uranium. And each gram of uranium, well, each nucleus of uranium undergoing fission will release this much of energy, 3.22 times 10 to the negative 11 joules. So the total energy released will be the energy released per fission times the total number of nuclei in 1 gram. Total number of atoms is the same as the total number of nuclei. And that is 8.24 times 10 to the power of 10 joules. Now, this is a tremendous amount of energy. Can you calculate how many kilograms of water can be boiled using this energy? Knowing that the amount of energy released, absorbed by water in boiling will be mass times specific heat times the change in temperature. You can do a rough calculation and see how many kilograms of water can be boiled. Now, nearly 250,000 kilograms of water can be boiled using that much of energy. So if you allow 1 gram of uranium-235 to undergo nuclear fission, the amount of energy released can be used to boil away 250,000 kilograms of water. So imagine if you allow 1 kilogram of uranium all of a sudden to undergo fission, how much energy is released. That is a bomb, isn't it? Well, we will discuss that as we go on. So at the moment, let's see what a chain reaction is. What is a chain reaction? Well, here I have explained what chain reaction is. Now, this is the first uranium nucleus absorbs a slow neutron or the thermal neutron, undergoes fission, produces fission products, and that fission product include 2 free neutrons. Well, if this is barium and this is krypton, 2 free neutrons are represented by these black dots. So a uranium nucleus absorbs a thermal neutron, undergoes fission, producing nucleus of barium, nucleus of krypton, and free neutrons, of course, a lot of energy. And each of these neutrons now can go and produce further fission in, say, at least 2 other nuclei, producing barium, krypton, 2 neutrons, barium, krypton, 2 neutrons, and these 2 neutrons in turn will produce fission in 4 different nuclei. And the neutrons released there will create fission in 8 different nuclei. You see how that spreads as a chain. Now, this is what is called the chain reaction in nuclear energy. So in a mass of uranium-235, if 1 nucleus undergoes fission, the neutrons that are released in this fission can cause fission in 3 or 2, depending on the number of free neutrons, different nuclei, releasing more neutrons. The generation of neutrons can produce 27 different fissions as we go on, and 81, and so on. So each of these neutrons, watch an animation of that chain reaction. Now what you see here is within a fraction of a second, the whole mass of uranium can undergo fission. Look at that. It doesn't take a very long time. So each of the neutron produce fission, further fission in other uranium-235 nucleus, releasing more neutrons, more fission, more neutrons, more fission, and it spreads right through the material within a very short time. Now, such a